Hi, everyone. Thanks for joining us today. It's a pleasure to have you. We're going to be talking about a new report and published paper called Commercial Wind Turbines and Residential Home Values, New Evidence from the Universe of Land-Based Wind Projects in the United States. So we've asked you to join in muted only mode, but we do want to hear from you. So please submit your questions via the Q&A window at any time. We will be monitoring them throughout the presentation. If questions come up of technical nature, we'll save the more content-related questions for the Q&A portion at the end of the presentation. Finally, I'll note that the presentation is being recorded. You might have heard that. And that recording will be shared with all registrants and participants, as well as the slides themselves. So don't feel like you need to screen grab anything. We'll be sending these over to you probably tomorrow, maybe the next day, and also anybody else that's registered for the presentation. We'll also be posting the same thing up on our landing page where this paper exists. And actually, if I can ask one of the panelists to just drop into chat that landing page so everybody has it handy. Finally, one quick thanks to the U.S. Department of Energy's Wind Energy Technologies Office. We couldn't have done this without their support, so we thank them for that. Thank you, Joe. Quick disclaimer, the views and opinions you'll hear today are not necessarily those of the United States government or the regents of the University of California, but rather those of the authors, and us alone. And talking about the authors, this is who is on the line with us today. I'm a research scientist at Berkeley Lab. My name is Ben Hohen. Joe Rand is also on the line, an energy policy researcher with LB&L. David Schwegman's here, an assistant professor in the Department of Public Administration and Policy at American University. And then Eric Bruner, a professor at the School of Public Policy at the University of Connecticut. So I'm going to be conducting the presentation, but during the Q&A, we'll open up the lines to the three of them as well. You'll get to hear their voices as well. Needless to say, this is a team effort, and David actually did most of the heavy lifting econometrically on this work. So just thanks to him for doing all that heavy lifting. I think it was a real pleasure to work with him on this project and look forward to future opportunities as well. So I'm going to go through some background and methodology and then talk about data and then dive into the results. So the first question you might be asking yourself is, why are we looking at wind energy and property values again? For those of you on the webinar, you might know that this is a subject we've studied in the past, in two published papers in 2011, 15, and 16 on the subject. But each of those papers had relatively small data sets. At the time, actually, it was the most data collected in the US, but relative to what has come since then and what we're presenting today, they're small data sets. But maybe more importantly, property values remain one of the top concerns for local communities that are considering hosting a wind energy project or have a wind energy project in their midst. Often, a home is a family's most valuable asset, and therefore protecting it and protecting its value is of extreme importance. So we can understand why it would be one of the top concerns. Additionally, sort of as we were waiting from the last time we published papers, a number of studies have accumulated in the European Union and found statistically significant impacts, those being UK, Germany, Denmark, and the Netherlands, for example. And as well, a recent study that came out of Rhode Island and Massachusetts found statistically significant effects near their wind turbines. And they found that those effects abated after 3 to 5 years and also were concentrated in the eastern, more populous part of the state. So this was a curious finding for us, given our past work of not finding statistically significant impacts. As well, you might be familiar with two recent solar property value impact studies, one of which was ours, that found that effects in those cases also modulate in the ex-urban versus rural areas. As well, you might be familiar with some of our past work conducting a survey of wind project neighbors. In that case, we found lots of things, but one of the more provocative things as it relates to this subject is that the individuals that moved into the community after the wind project was built were more positive toward the project than those individuals surveyed at the same time, but having lived there the whole time. So there seems to be some self-selection into communities of people with more positive attitudes. And finally, lots of data have accumulated since 2014, which was the last time our data sets closed. And as well, some of the methodologies that we'll be discussing today have evolved. And so we just felt like it was a good time to come back to this subject, and thanks to the Wind Office to giving us support for doing so. And that's what we'll be presenting today. So the model we're using is called a difference in difference model. It's the standard model for measuring event impacts with high precision and minimal bias. So let me try to break down this figure a little bit, and hopefully this will make sense enough so that when you see the results, those will make sense as well. So in this case, we're calling the event the announcement of the wind project. And we're examining the period prior to that announcement and also after that announcement. In this case, the control group of homes, the homes that we're using that we think are unaffected, are home transactions that occurred 3 to 5 miles away from a wind project. And we're using them as the control. And then we're looking at our target group of homes. And in the figures case, it's those homes between 0 and 1 miles from the wind project. Now, one of the first things we test is that they're acting similarly before the event. And that is what we found in our case. But then we're curious what happens after the event. And if the event has an effect on home prices, we might see a divergence of that parallel trend that exists prior to announcement. And this figure is showing that kind of thing, where the homes 0 to 1 mile decrease in value relative to their comparable group 3 to 5 miles away. Now, I'm talking as if this is the same project, and that is in fact what we did in our project. We are basically looking at this effect at the project level and then summing all those projects together to get an average effect across all projects. And I'll describe how that works in this next slide here. Let me see if I can get that to advance. So these are multiple projects, in this case 3 projects, that have different announcement dates in terms of the year that they were announced, but each of them has an announcement date. And in our case, we stack up these project announcement dates into that difference in difference model I just explained. So this stacked project timelines occurs in our data set. So we're looking at the announcement of each individual project as 0.0 in our data set. And then we're examining that period prior to announcement and after announcement. I mentioned that we had project level fixed effects. We're basically doing this experiment at the project level. We're breaking those projects into, we're looking at homes both near and far from that project and transactions that occurred before and after announcement. So that kind of gives you a sense of how it's a difference in difference, 2 sets of differences, both near and far and before and after. In the case of near and far, this is a depiction of one of the projects that was in our data set. This one is in Herkimer County in New York. And the far group, as I mentioned, were homes 3 to 5 miles away. They're shown outside of the blue area in black dots. The homes that are even further than that, 5 miles or more than 5 miles, are shown in red dots, and those are not included. And then inside the blue circle or shape are the near transactions. And we break them up into 3 groups, 0 to 1 miles, 1 to 2, and 2 to 3. We also additionally look at smaller denominations of distances, but that's the main focus, just those 3 groups inside of that near group. If you're really curious about how to write out what we're doing here statistically, this is how we do it. So we just include that for those individuals that are statisticians, but I won't spend any time describing this. So that gives you a little background and the methodological approach. Let's talk about the data we used for this analysis. So we started with a nationwide data set from CoreLogic of real estate home characteristics and transactions. This data set that we purchased from them is 122 million homes with 260 million transactions. It covers all of the residential transactions and homes in our country. And those are the ones that we're most interested in for this analysis. We matched them up geospatially with the locations of roughly 72,000 wind turbines that come out of LBNL's US wind turbine database. Some of you might be familiar with that. When we do that spatial matching and find homes within 5 miles of US wind turbines that transacted before the announcement and after the announcement, we end up with transactions that cover 30 states, 250 counties, roughly 400 wind projects, and 20,000 wind turbines. And it allows us to build a data set of over 500,000 transactions within 5 miles of those projects. In our case, the sales occurred 4 years before the announcement of the project and 10 years after the announcement. And so that 10 years after covers the period of construction and eventual operation of that project, and then beyond that. The data period is January 2005 through December 2020. That's when those transactions occurred. Yeah, and there's one other piece of data we'll talk about later on in the presentation that covers this rural-urban aspect that we also incorporated into our data set. So in this full data set, I mentioned we had around 500,000 transactions. The actual number is 496,000 transactions. And we've broken the data up into that near and far set of home transactions and shown the various characteristics, some of those characteristics on this slide here. You can see that the parcel size between those homes within 3 miles and those outside are pretty similar. Similarly, the building square feet of roughly 1,800 is pretty similar. The age of the building within 3 miles is a little older, about 60 years versus maybe 52 years old, and then so on and so on as we move down through the statistics. Now, you should know that we do concern ourselves with differences like the age of the building. That's important. That can influence the value of the home. In this case, older homes are generally worth a little less than newer homes. And so that might explain some of the difference in the adjusted sale price you see below. And there are other aspects of the characteristics of the home that might influence the sale price, and we control for them in our model. So we are concerned about those as well as other characteristics of the market and the size of the project and those sorts of things. Okay, so no surprise as you think of the geometric circles around an individual project, you're going to have more transactions as you move further and further away. There's just more land to have homes in there. And that's no surprise what we see in our data set. Most transactions are further away, but we still have plenty of transactions within 1 mile. And the actual numbers of transactions are shown in the table on the top right within those various distance bins and also in the various development periods, the pre-announcement, post-announcement, pre-operation, and post-operation. So in our case, we're really focused on that post-announcement data set, and inside of a 1 mile, we have almost 17,000 transactions, 16,000 transactions just in that small group there, which is an enormous number of transactions quite close to wind turbines. And as we move further away, no surprise, we get much larger sets of transactions to analyze. In the figure in the bottom right, we break those transactions that are in the table into just a figure that shows the percent of the total in each of the development periods. And what you can see here is that the numbers of transactions, or the percent of transactions in those various groups that occurred in the various periods that were within a mile of projects, equals roughly 4% in all cases. And this addresses one of the common concerns of these analyses that, oh, well, no homes transacted after they were announced or post-operation, so how can you analyze that? Well, in our case, there's really no change to the percent of transactions in any of the periods here. So things seem to be operating pretty normally, regardless of the fact that a wind project has just been built in their midst. So no rush to sell, or nobody's holding off selling, it appears. So that's my data summary, and now I'm going to step into the results. So this is one of the main figures that we presented in our announcement of this project. It describes one of the main findings pretty well. So in this case, we're looking at transactions within a mile of the nearest turbine, and we're comparing those values to those homes that are 3 to 5 miles away from the wind projects, around those same projects. You can see that the announcement period is shown in the dashed vertical red line, and that effectively is the beginning of our period where, or the effect, as I mentioned earlier, where we're starting to potentially, we wondered, see effects. And sure enough, that's what we find. And as I mentioned, the period after announcement encompasses the construction period and then ultimately the beginning of operations. But in the first part of that period, there is no construction of the wind project. It's not generally announced and then immediately constructed. It's otherwise announced, and there's deliberations in the community. Ultimately, decisions made in the case of all the projects in our data set that that project should be built, and it is built, and ultimately begins operations. So in this case, we see a dipping of values after the announcement of the project that kind of bottoms out right around the ending of construction and the beginning of operation, and then begins to trend upward, returning to pre-announcement inflation-adjusted levels 3 to 5 years after the wind project begins operations. So if you average that whole post-announcement period, in this case, within a mile, it's around 11% dip during that whole period. Obviously, it goes a little below that in that post-announcement pre-operation period, but then returns to, as I said, more normal levels or pre-announcement levels after that. So that's within a mile. Clearly, we see statistically significant impacts here that seem to be related to the announcement of the project. When we look between 1 and 2 miles, we see a lot less evidence of effects. Remember, we're still comparing these transactions to homes 3 to 5 miles away. In this case, if you look at this event study, you don't really see many periods that are statistically significant. But if you average across the whole set, in some cases, depending on the model approach we use, and I'll show them in a moment, the effect is around 3% of an average impact between 1 and 2 miles. Finally, if we look between 2 and 3 miles now, we don't see any statistically significant evidence. And similarly, when we kind of accumulate the entire post-announcement period, we don't see a statistically significant effect for homes in that distance band as compared to homes 3 to 5 miles away. So I mentioned that we also break the transaction groups, the distance groups, down into smaller denominations, if you will, and that is what we're showing here. In this case, we're averaging the entire post-announcement period, and remember, within a mile, on average, that was around 11%. But in this case, we're looking at 3 groups of transactions within just that mile period, that mile group, within the half mile, between a half mile and 3/4 of a mile, and between 3/4 of a mile and 1 mile. And beyond that, we step out in 0.25 mile or 1/4 mile steps all the way out to 3.25 miles. And you can see, as we would expect, if homes values are being affected by something that they are close to, you would expect that as they move further and further away from that they would see smaller and smaller effects, and that's in fact what we see in this figure. Now, you might be looking at that effect between 0 and a half mile and scratch your head. In a way, we were too. One would expect if people are reacting to proximity to something, the closer you get, you'd see more pronounced, more negative effects in this case. That's not what we see. In fact, what we see are some ambiguity in terms of our effects. And in this case, that group of transactions that occurred within a half mile results in a not statistically significant effect. The margins of errors around that are too large for us to tell you with any statistical certainty that there is an effect there. Now, that could be there for a few reasons. One, we don't have as many transactions within a half mile, so the margins of error are generally larger. But there also could be other things going on. For example, homes in that distance bin might be receiving some compensation from the wind developer and owner, and that might transfer to the new buyer, which would encourage them to potentially pay more for the home. There are a number of reasons why that might be the case, but we just aren't seeing statistically significant effects when we look across the full sample, which is what this does. If we take some of the tables that the figures we previously saw and show it in a table, that's what we're doing here. And I mentioned we had a variety of different approaches to test whether our results were stable. And we're very open about that. These are the various models we used. They are described in lots of detail in the paper. But the point is, if you will just focus on this top line of 0 to 1 mile, you'll see that the average effect that we estimated in the model that we prefer, which is around 11%, is also found in every other model, give or take maybe 1% or so. So regardless of how we structure the model and what kind of controls we have in there, we're finding a pretty stable result here. And similarly for the transactions that occurred 1 to 2 miles away and those 2 to 3 miles away. In some cases, the 1 to 2 miles is statistically significant, shown here by the multiple stars following it. And in some cases, it's not statistically significant, shown here without the stars. But inside of a mile, it's always highly statistically significant difference here for those home transactions within a mile versus those 3 to 5 miles away. We also looked at a variety of other methods to test the robustness of our result. And one of the ones that we discuss in more detail in the paper, which I won't discuss in as much detail here, is what we call a falsification test. But a quick description of it is we basically just take a county that has no wind energy developed in it, but has similar wind speeds and otherwise is similar to the counties that were in our data set. And we plop a kind of random point in that county and then wrap our distance bands around it and measure home value changes over time with a fictitious announcement date. So this is sort of a preposterous way to do it in terms of actually finding something. But what's interesting is that you find how much how much randomness is in a random point of transactions in our country in areas where there's lots of wind. And those are depicted here in the various shades of blue, the lower, average, and upper bound. And you can see that they range from around -5% to a little bit more than 5%, with the average estimate being very close to 0, as you would expect. There shouldn't be any difference related to a random point a mile away, homes from a mile away from a random point versus homes that are 3 to 5 miles away from a random point. But in our case, where we did have a wind project within that distance, we find a very clear statistically significant effect that's outside of those error bounds and those upper and lower bounds. So that's one of the falsifications test we did. The second one is including the top and bottom 1% of sale prices and also home foreclosures in our data set. It is normal to exclude them from data sets, but some people argue, well, that's where you're going to find an effect, because maybe those heavily discounted homes are where you can't exclude them because that's maybe where there is evidence of an impact. But when we include them, we don't find any difference in our results either. So that isn't an explanation that's valid in our case. So regardless, I mean, these are the various ways we took testing our results seriously, and we found very similar results across our data sets and methodologies. So now I'll turn to this question of urban and rural counties, which is the last piece of this presentation today. So as I mentioned at the top of the presentation, a number of other researchers had found this sort of interesting result that property values seem to be more pronounced. The impacts to property values were more pronounced in areas that are more urban versus areas that are more rural. And so we wanted to look at that same thing as well. And we used the USDA Economic Research Service rural and urban continuum codes to divide our various counties across our data set. We defined the urban counties as counties in a metro area of roughly or more than 250,000 people. That doesn't necessarily mean the county itself has more than 250,000 people, but rather it's in a metro area amongst a few counties that have that number of people in it. And if you weren't in that group, then you were considered rural in our case. So those could be counties and metro areas with fewer than 250,000 people, or a separate distinction, counties with less than 20,000 individuals that are adjacent or not adjacent to a metro area of any size. So that constitutes the rural group. And across the entire US, regardless of whether there's wind energy developed in those counties, 77% of the counties are rural and 23% are urban. In the case where there are wind energy facilities in those counties, 82% of them are rural and 18 are urban. And in the case of our analysis data set, it's 81% rural and 19% urban. And I'll just note here that there were some projects that were built that just had no transactions near them, so we couldn't include them in our transaction data set, and that's why some of those numbers would be different. This is a map of those same counties I just mentioned, counties with wind and without wind. The ones that are urban are a blue shade, and the ones that are rural are kind of yellow or green. The bolder colors are counties with turbines, and you can see kind of how they're distributed across the country. There are lots of counties in the center of our country that are rural, that have wind energy in them, but there are plenty of counties sort of across the Great Lakes and up into the Northeast that are also rural, that are, by our definition, that have wind turbines. And similarly, there are plenty of urban counties in the Northeast and also in the center of our country. And so we felt like this was a pretty safe bet here to divide this group up. We aren't necessarily excluding one part of the country for the benefit of the other when we do this. We're just simply including areas that are closer to those metro areas around wind projects across our country in each of the states. So when we talk about urban and rural counties in the rest of this presentation, these are the counties we're defining here where we see wind development. This is a similar set of results that you saw before in that longer table where we had a variety of different models we were testing. In this case, we're using the two preferred models I mentioned on the far right that we felt like were the most parsimonious, meaning fewer sets of controls, but still operated just like every other model that we had in our data set. And in this case, we see that the results within 1 mile for the urban sample are very different than the results within mile in the rural sample. The numbers of transactions in those two groups are shown there on the third to bottom line. And what we can say here is that in the case of the rural sample, where we have 135,000 transactions in counties in metro areas with populations less than 250,000, we see no evidence of an adverse impact of homes in that distance band as compared to transactions that occurred around those same projects in those same counties 3 to 5 miles away. But In the case of the urban sample, we clearly see a statistically significant impact. And in fact, that impact seems to extend out to 1 to 2 miles as well, regardless of the model we use, whether it's model 1 or 2. So this aligns with some of the results that had been found by others in Rhode Island and Massachusetts in the case of the wind energy facility analysis they did, and as well as some of the solar energy analysis that we did and others as well. Now, I had showed you previously an event study and also the breaking down into smaller distance bins of the full set of results post-announcement. And in this case, I'm breaking them up into the urban sample and the rural sample. Urban sample is on the top, and you'll see that that event study on the far left, which is figure 1, looks very similar to the event study we showed for the full sample of results, because now it's apparent that this is what's driving the full set of results, that urban sample. But when we look down from that on figure 2 for the rural sample, that event study shows, basically nothing that's statistically significant. Not surprising, given the fact that the results I showed you on the previous slide also are not at all statistically significant. So we don't see evidence of an impact in that rural sample in the event study either. Similarly, when we move to the average effects post-announcement in these smaller distance bins, we see a very clear, pronounced effect as we get further and further away from the closest turbine in figure 3 on the top right, and no such relationship in figure 4 in the bottom right. You will notice now that the 0 to 5 mile effect is statistically significant at both the 90 and the 95th confidence interval level, which means we are finding an effect within a half mile that is statistically significant. The error bars are still larger. There's still more noise around that estimate, but in this case, it is statistically significant. And I think what's interesting is that it's not dramatically lower than the effect we are seeing within a half mile and 0.7 miles, which might be evidence of the kind of thing I mentioned before, where some of the homes are selling for actually a little bit more because maybe they have payment that it travels with the deed. We're not sure about that, but clearly there's no evidence of a dramatically lower effect in this case within a half mile in that urban sample. So that brings me to the conclusions, which is the last slide before we open it up for Q&A. We analyzed an unprecedented set of 500,000 transactions near US wind turbines in the United States. For homes within a mile, we find a wind project. For homes within a mile of a wind project compared to homes 3 to 5 miles away, we find an average reduction in home sale prices of approximately 11% after announcement, and weak or no effects appear beyond that distance. For the full sample, effects for homes within approximately 1 mile begin an average of 3 years before construction starts after the announcement date, with homes continuing to decline through project construction and then returning to inflation-adjusted pre-announcement levels 3 to 5 years after project operation commences. Importantly, impacts that we find are only apparent in more populous US counties, those in metro areas with greater than or equal to 250,000 people. And then I'll just note this second to last bullet here, although I didn't talk about it today, our paper does reference this set of analysis we did, which is that impacts were not apparently related to the size of the wind project, both in terms of the capacity or the number of turbines. So something's happening that's independent of those, at least based on our results. Now, one big caveat you should know about this work is that we set up our model to compare homes close to turbines to homes that were further away from turbines around the same wind project. So in all cases, we're looking at transactions that occur within 5 miles of a wind project. But I think there's a real possibility that there are some differences between transaction values within a wind project as compared to transaction values away from all wind projects. And for example, there is evidence of work we've done and others have done that show increased local tax revenue and worker income and employment in areas where there is wind development. It's not a crazy idea that some of those effects might be capitalized into home prices. Often those kinds of things are capitalized into home prices. Our analysis did not answer that question. And so we think it's a good thing to do in the future, but something we can't talk about today. As well, I mentioned that we looked at project size and capacity, the number of turbines, but we did not take into account whether a home can actually see a wind project. It has been found in past cases that wind energy facilities that can be seen from a home have unique impacts. That is something that we did not do, and we hope to do that in the future. So with that, I'll leave you with this informational slide, and we'll open it up for Q&A. So if the rest of the panelists will turn their cameras on and unmute yourself, we can go through the questions. And Joe, you want to lead us through those?
Yeah, sure. I'd be glad to. Thanks for the presentation, Ben. And before I dive in, I would encourage anyone to submit more questions to the Q&A. I'm seeing a few good ones here, but keep them coming. So I guess maybe first, let's start with talking a bit more about the methods. Ben, in one of the early slides, you talked about the evolution of the work and your previous studies and that came out in 2011, 15, and 16. And you kind of focused on the data and the number of transactions in those, but there's also been an evolution in terms of methodology. So, I guess I'd ask you to speak to that as well. And then the question specifically says, are there any changes you would have made to the methodology that was employed in this study to increase the confidence in these conclusions?
Yeah, that's a great question. And I'll have some of the other panelists, Eric and David, also chime in here. So I'll go back up to earlier in the presentation here. We're using this stacked difference model. I think the improvement we've made is this stacking. In the past, we generally did not stack like this and have individual transactions, individual projects analyzed before and after and near and far, but rather accumulate projects together. And so that is a criticism of the difference in difference approach that had existed prior to this that we adhered to and aligned our work with that criticism of this work. Would that have changed our results? I don't know. I think that we have an order of magnitude larger number of transactions now than we did before. So we'd still be running into issues of larger confidence intervals around our estimates that might not have exposed effects. But one of the things and also if we had used the old methodology with our current data set, would we have found statistically significant effects? I don't know. I'm not even sure if we tested that. But I will note that once we had these results, I went back to our older papers and looked at some of the results. And actually, the coefficients in the post-announcement pre-construction period are usually lower than the estimates in the post-construction period. This would be some sign maybe that there was a dip happening, but we just didn't have the model power to be able to discern those differences in those two time periods. So we couldn't have done it then and had enough data to potentially do it now. So that's a few filling in a few pieces there. I don't know if David or Eric, you guys have anything to add.
I think you handled that. That was all correct. Yep.
Great, thanks. Well, I guess this is sort of a related question on methods as well. The overall effect, Ben, that you talked about of 11%, of course, kind of averages across the full data set. And I think this person is asking whether there was any analysis at a more regional level. Of course, we controlled for census tract or zip code in the model, but is there any reason to believe there might be an impact in certain states or regions?
Yeah, I mean, our breakdown was based on urban and rural. Because we're analyzing things at the project level, we have a more difficult time breaking the data down much further, because we're really controlling for those inter-project effects. And so we chose to do this urban or rural effect. I guess I would ask the questioner, what hypothesis does he have or she have as to regional effects? If there's something that we could use as a proxy for whatever effect they'd like to find in that might differ by region, we can test for that, or we could potentially do that in a future paper. But this urban rural, it felt like because of these other papers, was good to look at. I don't have any preconceived notion as to why home transactions in Ohio would be different than in Pennsylvania or Connecticut versus Indiana. But if the questioner does have more information about that or a hypothesis, it might be worth thinking about that. And I should also note, we're honoring what's in the literature. Others have found these kinds of effects. We're going back and testing that, whether they exist too. I think our paper is the one that's very clearly showing this big dip after announcement and into operations across the full country. And that was something that others had not found. So anyway, that's my answer. Yeah, anything else you want to add?
Ben, can I just jump in real quickly? We did actually look at regional effects. It got removed because we didn't have enough room in energy policy because of the space constraints. But what those results showed is that the results were pretty homogeneous across regions. So we found similar results in all 4 regions of the United States as defined by the census. And so, in other words, nearly all the results were within the 1 to 2, the 0 to 1 mile range. And they were relatively considered, you couldn't reject the null that they were the same across the 4 regions.
Thank you for that. Yeah, that's something we did not publish in the paper. Actually, it's a really good point. I think we noted that in footnote in the paper. Is that correct?
Mm-hmm. Yes.
I think that's correct.
Okay. Yeah. But they are noisier effects for sure. And especially if you broke them down into the urban rural, you'd have, 8 distinct groups here.
Yeah, it's footnote 7 for anyone who's interested.
Thank you, guys.
Excellent. Well, just kind of riffing a little bit more on the urban-rural distinction. James Palmer here asked a great question that, defining urban-rural at the county level isn't especially fine-grained, and maybe there would be, higher resolution ways to do that. For example, using the National Land Cover data set to look at land cover across the U.S. to identify highly urbanized areas. Is there, do you guys think that would be an improvement to this work? Is that feasible to operationalize that?
Yeah, I can address that. I think that's a great suggestion. As Ben has mentioned, we're going to be doing a few additional projects, potentially looking at something like visibility, which I know is one of the other questions. And yeah, we could absolutely incorporate that into an additional analysis. So thank you for that suggestion.
Excellent. Yeah, I'm seeing here a couple of different questions about the turbine size, specifically maybe hub height or swept area or tip height. So one person, for example, says newer turbines might be close to 300 feet tall, whereas we've seen kind of older turbines, and many that we encompass in our data set here might be more, like 350, 400, 500 feet tall to the total tip height. Is there any reason to believe that those variables, hub height, swept area, tip height, would influence this impact?
Ben, you want to get to that, or I can address that?
Why don't you take a stab, and then I'll see if I have something to add. I had something to add, but I think it's less important than what you're going to say. So let's.
Okay, thanks. No, great. It's a great suggestion. We actually did a lot of heterogeneity analysis to try to explore this question. And the thing to think about with our methodology is that we are using within project variation to identify our effects. So we're comparing transactions, as Ben has noted several times, 0 to 1 miles, 1 to 2 miles, and 2 to 3 miles, compared to transactions 3 to 5 miles away from the project. So in order to look at something like hub heights or the size or anything like that, we need within project variation in that height. And not many of these projects, a lot of these projects had like similar sized turbines, maybe one or two that had been retrofitted that might have gotten a little taller or something like that, but there wasn't a much variation within projects to identify any of those effects. But again, we're going to be doing some work looking at visibility, and we might be able to segment projects in the future to think about, okay, looking at, you know, more homes that have a greater line of sight because of the size of the turbines, for instance. So we can look at that heterogeneity, hopefully in future work. But it is something we really are interested in exploring.
Yeah, and the other point I'll make is, as some of our work has found, you know, there's a very clear relationship between the increase in turbine height and the numbers of turbines that are in the same land area. You know, our analysis found is turbines that are, we called them at the time future turbines, but they really are the turbines that are being installed now, are almost 60% taller than turbines installed in the decade before when we did our paper, which was a few years ago. And the amount of turbines put in the same land area was 60% fewer as well. No surprise, you know, you just, as you have a bigger turbine, you need to set it back from other things, the property lines, other turbines, roads, homes, that sort of thing, more. Because there's safety risks there. So it will be interesting to be able to try to compare and contrast those competing effects. It isn't as if all turbines in a project are larger, and they're the same number of turbines. There are fewer turbines, but they are taller. So how to tease out those differences isn't quite clear, but maybe some of that visibility analysis will allow us to do that.
Yeah, excellent. And on that subject of the visibility analysis, there is a question here about, you know, how does one go about operationalizing that? How do we look at visibility or line of sight from a home that's transacted to the turbines?
It's not settled science, that's for sure. So we're working with the United States Geological Survey, and we heard a question come in from Mr. James Palmer. He is also working with us on this subject, bringing in the landscape architecture and the visibility analysis aspects of the trade. And we are attempting to build a model that allows us to fairly accurately predict from a home whether turbines can be quote unquote seen from that home. We can't model everything perfectly in a line of sight model, because there are going to be trees, single trees, for example, that might break a view that we wouldn't be able to capture. But we hope to do pretty well at it, at least directionally, so that we have a pretty good sense as to whether a home is seeing lots of turbines versus a home that's seeing none. And then we have a variety of other aspects we'll be looking at, not just seen or unseen, but, you know, the degree to which many turbines can be seen and how close those turbines are, whether they're surrounding the house, the sense of looming. These are all things we're exploring. And we did some field work earlier this year with 7 individuals going up into the Tug Hill Plateau area of New York to try to characterize some of these things in real locales. Like, we were standing around projects and in amongst the turbines and gathered some data from this set of individuals as to their impressions of those different situations or viewpoints. So we're trying to kind of build a model that does a good job of predicting those senses and maybe qualitative aspects that we are finding in the field. Still a long way to go on that, but we're moving forward, and hopefully we'll be able to advance the literature on this. I will say that previous studies have simply just used like a 1 or 0 binary, you can see it or you can't, line of sight model, or they've just simply used a point in the middle of the wind project and estimated whether a home can see that point, which isn't accurate either. So there's lots of levels of success here and various ways of approaching the problem. We hope to provide a more rigorous, the most rigorous method But you're still never going to be perfect. But hopefully we can be close enough to see if there is a relationship here.
Great, thanks. Yeah, I think there's an interesting question here just about the makeup of the data. And, when we talk about an overall effect, maybe 11% in that post-announcement period. But we know from, I think it was a later slide, Ben, that actually the majority of the transactions did come from what we classified as urban counties. So this person calculated it to be 72% or so. Yeah, I think we had 360,000 transactions from these urban areas, and maybe 135,000 transactions from rural areas. So yeah, to put it succinctly, the majority of our transactions are coming from urban counties. Is that potentially kind of influencing the average effect when we also know that the majority of wind development, especially on a capacity basis, is in fact in rural counties?
Ben, you want?
No, go ahead.
Okay, yeah, no, it's a great question, and it's to some extent a limitation of the study with this sort of approach to try to control for bias that might come from within different housing markets. What we need to estimate our models is housing markets with sufficient transactions, across space and before and after the announcement of the wind project, in order for these transactions and these sort of models to be identified, meaning in order for us to actually have sufficient variation in housing transactions to identify effects on sort of the announcement of this project and sort of the installation of this project on home values. So as a result, we actually can't really use this type of model in more rural areas where there just aren't sufficient transactions, near and far from a turbine and before and after the announcement of a turbine. So it's a great question. And that says, one thing that Ben has sort of alluded to is that, these results don't necessarily speak to how any individual wind project will affect a home in any particular community. It's really just a national average about thinking about these effects.
Yeah, and as well, if there are no homes near a wind project, that home is those homes that don't exist aren't impacted. So we did the best we could to break the model up into these two cohorts, in part because we saw really big differences in the results here. So it's a step forward in terms of understanding a possible difference here. This is so stark that one really has to wonder what's going on in the urban group as opposed to what's going on in the rural sample. And I'll just theorize, as we have done in the paper, that others have found, again, these results between urban and rural samples, and as well theorized through looking at survey literature, that maybe the value that individuals in urban contexts place on the environment are different than those in the rural sample. We can only hypothesize that might be the case, but clearly we are seeing a difference here. And if that were the case, then maybe, and the theory is place attachment or place congruence, individuals have a view of turbines that is more congruent with the way that they attach themselves to the environment or that place in a rural sample, and not as congruent in the case of the urban sample, which is why they're so affected by these the presence of turbines in those contexts, meaning the buyer and the seller both agree this shouldn't be there, where in the case of the rural sample, the buyer and the seller seem to agree it's fine that this there, it's not going to change the home price relative to homes further away. So a lot to be unpacked here. I think there's more research to be done, but clearly this is an effect that not only we have found, but others have found, and there is something to it. So again, but I'll reemphasize what David said. We can't talk about individual projects. That wasn't the purpose of this work, but this is undeniably the most rigorous statistical analysis of transactions around projects in our country. And it's so much better than an individual analysis around a single project that has a few transactions where you can get all kinds of reasons for error. In our case, we can kind of rule them out given the large sample and the statistically consistent results across our various model specifications. So we are running out of time, Joe. We've got maybe a few minutes here. I want to do a little closing remarks, but maybe if we have time for one question or so. And I'll just note that any questions that don't get answered live, we will try to answer virtually via email after the presentation.
Yeah, excellent. Well, yeah, let me just, there are a few more questions trickling in. I'll just pick one that I think is provocative here. Matilda asked about repowering. There has been, as projects age, there's an increasing trend toward, retrofitting or partial repowering of certain projects and even full repowering. And especially because we found an effect kind of post-announcement that then mitigates as the project continues to operate. Would we expect to see potentially another effect after a repowering announcement? And then, Matilda asks about variables that might influence that, changes to turbine height, maybe the array of turbines, or the local perception of how long that project would actually be in the community. So any thoughts or reactions to that?
I think those are great questions, Matilda, always asking good questions. I think that's going to have to be another study. Number of things that might be different about projects that are built for the first time in a community versus those that are retrofitted in the same community. So I'd only have to hypothesize as to what might be the differences there. Good question, should be looked at. Should we leave it there? All right, great. Well, thank you all for joining us today and asking such great questions. And as I mentioned, we will be sharing these slides and the recording today with you in the next few days, and as well answering questions that have not yet been asked via email after the presentation, assuming you didn't ask them anonymously. If you didn't do that, we will take a stab at answering them via email. So thanks, everyone. Have a great day and a good Christmas holiday.